Welcome to this explainer. All right, jump right in with me and picture this. You are the lead engineer on call for a massive e-commerce platform. It's Black Friday, traffic is absolutely surging, and suddenly the support tickets start pouring in. Users can't check out, their payment carts are timing out, so you crack open your laptop, bracing yourself for an absolute disaster zone. But instead, you see something terrifyingly calm.
It is 2 a.m., your phone buzzes. The dashboard is a wall of green, yet the error tracker is filling up with user complaints. This right here is the ultimate 2 a.m. panic moment. Your CPU is totally nominal, memory's fine, disks are healthy, and all your standard health checks are passing with flying colors. Everything looks perfectly, beautifully healthy. But the reality is, absolutely nothing is working. Standard monitoring has completely and utterly failed us.
So we have to ask a really critical question. Why are your dashboards green when your users are completely offline? Think about it. If monitoring is your system's smoke detector, what on earth do you do when the house is burning to the ground, but there is absolutely zero smoke? This terrifying reality is what we call the observability gap. And understanding exactly how to cross this gap is what separates junior developers who rely heavily on pre-built dashboards from senior backend engineers who actually know how to interrogate a complex system.
Okay, Section 1, the green dashboard nightmare. Let's look at why this happens.
To understand why standard monitoring blindsides us so badly, we really have to look at the chaotic state of modern microservices. We aren't building simple monolithic applications running on 3 bare metal servers anymore, right? We're orchestrating hundreds, sometimes thousands, of interconnected ephemeral services. In these hyperscale environments, a single user checkout request might traverse 15 different microservices, hit 3 message queues, and query 4 distinct databases. When an incident happens in this massive web, the system rarely just crashes outright. No single component is hard down. Instead, emergent properties cause a cascading failure. Maybe a subtle config change in service A causes aggressive retries in service B, which eventually cascades into database connection pool exhaustion. The system is not crashing, it's just moving in slow motion. And the scary part, you lack the visibility to see exactly where that friction actually is. Now, a junior engineer might look at these exact symptoms on a dashboard and see a perfectly healthy system. They see safe CPU limits, zero database row contention, and think, hey, we're good. But a senior engineer, they recognize the silent killers. If your synthetic latency probes are timing out at exactly the 30-second mark, and your application logs show a highly suspicious 29-second gap between entries, the process isn't computing, it's waiting. It's friction hiding somewhere in the network path, maybe an invisible application lock or a really subtle off-CPU scheduling delay.
That brings us to Section 2, monitoring versus true observability.
To fix this blind spot, we need a hard paradigm shift. We have to move from merely reacting to known failures to actively investigating complex emergent behaviors. So the crucial point here is that monitoring is really just a subset of true observability. Monitoring is excellent for known unknowns, the stuff you expect and can easily measure. You set a threshold, and when reality deviates, you get an alert. It simply answers, is X healthy? Observability, on the other hand, deals with the unknown unknowns. It is custom-built for failure modes you've never even imagined. It answers the highly specific, ad hoc question, why did user 4821 see a timeout on this exact transaction on this specific node at exactly 2:04 a.m.? Formally speaking, observability is the ability to determine the internal state of a system entirely from its external outputs and telemetry data. Look, when a request traverses hundreds of microservices, guessing the failure mode is just mathematically impossible. You can't just stare at a black box and hope the answer magically comes to you. You need high-fidelity telemetry that peers directly inside that black box and tells you the exact truth. And this telemetry rests on 3 foundational pillars. First, logs. These provide the narrative record, timestamped events that tell the granular, step-by-step story of a request. Then, metrics. These provide the quantitative pulse, scalable, aggregated numerical health data over time. And finally, traces. These are your distributed detectives, showing you the end-to-end request waterfall across service boundaries. But here is the real secret. If you isolate these pillars, you leave massive, critical blind spots. They absolutely must be correlated. Metrics tell you there's a problem. Logs tell you what the problem is, and traces tell you exactly where it happened. Let's dive into Section 3, the OpenTelemetry standard. For a really long time, correlating all this data meant locking your entire architecture into a single, highly expensive vendor.
But the industry has finally matured, bringing these three pillars together under one great unifier. Enter OpenTelemetry, or OTel. It's an industry-standard, vendor-agnostic framework for generating, collecting, and exporting telemetry data. To give you an idea of how massive this shift is, OpenTelemetry is currently the second largest cloud-native computing foundation project in the world, literally right behind Kubernetes. OTel decouples your instrumentation from your backend observability tools, meaning you don't have to rip out all your application code if you ever decide to switch vendors. Huge win. And this brilliantly illustrates why it's such a structural shift in engineering economics. You get auto-instrumentation across all the popular languages, a single OTel collector proxy to process and route your data, and a universal protocol called OTLP. Because everything shares a common trace ID context, the workflow is basically magical. You can click a latency spike in a metric chart, instantly see the associated error logs, and immediately open the full distributed trace. You invest exactly once in instrumenting your services, and you can export that pristine data anywhere you want. Section 4. Surviving the data cost trap. Because, unfortunately, this visibility is definitely not free. Let's speak candidly for a second about the harsh financial realities and the true cost of engineering visibility at scale. As microservices proliferate, telemetry volume grows superlinearly. More services mean more network communication, which means an absolute explosion of traces, logs, and metrics. Companies regularly wake up and discover they are spending 35% of their entire cloud budget simply on observability tools and data storage. If you aren't ruthlessly careful, your telemetry bill will literally outgrow your actual infrastructure compute bill. Congratulations, you are now a data storage company that occasionally sells e-commerce products on the side. To survive this, senior engineers use ruthless pragmatism with data sampling. You've got head-based sampling, which randomly grabs, say, 10% of traffic right at the start of a request. It's very cheap, sure, but when a critical 500 error happens, there's a 90% chance you just dropped the evidence. Then there's tail-based sampling. This buffers the whole trace in memory at the collector, literally waiting to see if an error actually occurs before deciding to keep it. It retains 100% of your errors and maybe 1% of successful baseline requests. Yes, it costs a bit more RAM to run those collector pods, but it masterfully balances pristine visibility against soaring infrastructure costs. Now here is a trap that catches almost every single scaling startup out there: cardinality explosion. Never, ever use a high cardinality value, like a dynamically generated user ID or a session token, as a metric label in systems like Prometheus. If you have 10 million users, you literally just created 10 million unique time series data streams in your metric database. It's an absolute storage and query disaster that will choke your database and spike your bill overnight. Just don't do it. Put those unique user IDs in your logs or your trace attributes, never in your aggregated metrics. All right, moving into Section 5, hidden bottlenecks and trade-offs. Let's move straight from the data cost trap and into the trenches. We're going to look at some real-world production nightmares and the architectural trade-offs that usually catch junior engineers entirely off guard. Take random Kubernetes pod restarts, for example. A junior engineer might blindly blame the developers for a bad code push, but a senior engineer formulates a strict hypothesis pipeline based on system behavior. Node is healthy? Check. Application logs are completely empty right before exiting? Check. If there is no unhandled exception printed to standard out, the kernel terminated that process instantly. You should always suspect the Linux kernel OM killer, the out-of-memory killer, ruthlessly enforcing your container boundaries. Senior engineers actively hunt for specific architectural blind spots, just like these. For instance, are you running a service mesh, like Istio? Well, the heavy telemetry reporting from those sidecars actively steals CPU time from your actual application worker threads, which causes massive long-tail latency. What about adding large buffer annotations to your Nginx ingress to handle file uploads? If you get 50,000 active WebSocket connections, Nginx pre-allocates that massive buffer per connection and instantly OM kills your entire cluster. And always remember off CPU bias. The slowest code path isn't always doing work. Very often it's just sitting there doing absolutely nothing, waiting on a thread lock or a downstream network call. Finally, Section 6, the senior engineering mindset. Let's see how all of this builds together. Because the ultimate fix isn't just buying a better monitoring tool, it's a fundamental shift in how you view system architecture entirely. 15,000. That is the number of lines of code a truly senior developer might just delete in their first month on a new project. While junior engineers focus heavily on shipping new features and adding more and more complexity, senior engineers recognize that their value is actually inversely proportional to the amount of code they write. Every single line of code is a liability just waiting to break at 2 a.m. This right here is the art of strategic deletion. It's about systematically reducing cognitive load across your entire team. Delete redundant code patterns, rip out unused features that are only creating false complexity. Eliminate those massive premature optimizations built for hyperscale scenarios that simply never happen in real life. Drop heavy third-party dependencies if you're only using 5% of their functionality. I literally cannot emphasize this enough. Reducing complexity is vastly superior to writing new logic. Because at the end of the day, humans are the ultimate bottleneck. Research consistently shows that operator error, bad deployments, misconfigurations, flawed mental models is the leading contributor to user-visible failures. And it is the single most difficult failure to mask through traditional system redundancy. You can't just throw more servers at a flawed human mental model, right? That is exactly why deep observability, strict automation, and ruthless simplicity are absolutely non-negotiable at scale. I'll leave you with this provocative thought to take back to your engineering teams. Are you building systems just to ship more code, or are you building systems that tell you exactly why they broke? Visibility must precede modernization. You cannot safely accelerate a system that you do not fundamentally understand. Audit your telemetry, instrument your blind spots, and start treating observability as a core feature, not just an afterthought. Thank you for joining this explainer.